Let us first place today's lecture in the overall course flow. We started from the fundamentals of petroleum engineering, then moved through petroleum geology, geophysical methods, drilling, petrophysics, well logging, reservoir engineering, reservoir modeling, reservoir simulation, and recovery methods. Today's topic, subsurface and petroleum data analysis, fits naturally into the production stage and connects all the earlier topics together. You can think of this lecture as a bridge. Earlier lectures taught us where the data are created. Today, we focus on how to use those data. In other words, geology gives us structures, geophysics gives us subsurface images, drilling gives us direct measurements, while logging gives us continuous downhole information, reservoir simulation gives us predictive outputs, and production operations give us time series field performance. Petroleum data analysis is where all of these come together. Today's lecture is organized into 5 main parts. First, we begin with an introduction to petroleum data analysis. Second, we will examine conventional methods used in petroleum data analysis. Third, we continue with current methods and field-scale workflows. Fourth, we will discuss future trends, especially digital oilfield concepts, machine learning, and generative AI. Finally, we will finish with recap, key learning points, and what comes next. As you listen, I would like you to ask yourself a simple question. How does data become engineering knowledge? Because that is really the heart of today's lecture. Let us begin with a very simple but powerful question. What is petroleum data analysis? Petroleum data analysis refers to the tools, techniques, and methodologies that use actual field measurements as the starting point, the building blocks, and the foundation for analysis, workflows, modeling, and decision-making. This definition is important because it tells us that analysis does not start from imagination. It starts from evidence. It starts from measurements. It starts from what the field is telling us. Engineers do not just make guesses. They interpret signals from the subsurface and from production systems. An interesting way to think about petroleum data analysis is this: the reservoir cannot speak directly to us. It does not tell us, "Here is my porosity," or "This is my pressure support mechanism," or "This area still has unrecovered oil." Instead, the reservoir sends us clues. Seismic amplitudes are clues. Well logs are clues. Core data are clues. Pressure transient data are clues. Production decline is a clue. The job of the petroleum engineer is to collect these clues and turn them into understanding. This slide asks a very basic but essential question: where does the data come from? In petroleum engineering, data are generated throughout the whole field life cycle. we obtain data during exploration, drilling, appraisal, development, production, monitoring, and sometimes abandonment planning. For example, during exploration we get seismic data and geological interpretations. During drilling, we obtain mud logs, wireline logs, drilling parameters, formation pressure measurements, and cuttings. During appraisal and development, we collect core data, SAL data, well tests, fluid samples, pressure data, and static reservoir information. During production, we obtain rate data, water cut, gas-oil ratio, pressure depletion trends, injection data, and facility performance. So petroleum data are not created in one moment. They accumulate over time. This means one of the biggest engineering challenges is not only collecting data, but also integrating different types of data that were acquired at different times, with different resolutions, and for different purposes. This slide asks another good question: how do petroleum data look? The answer is, petroleum data do not come in only one format. Some data are images, some are logs, some are tables, some are curves, some are maps, some are 3D models, and some are time series. This is one reason petroleum engineering is such an interdisciplinary and exciting field. A geophysicist may work with seismic cubes. A petrophysicist may work with depth-dependent well logs. A reservoir engineer may work with pressure histories and production rates. A geologist may work with facies maps and stratigraphic frameworks. A simulation engineer may work with grid properties, input decks, and forecast outputs. So when we talk about petroleum data analysis, we are not talking about one simple spreadsheet. We are talking about a very rich ecosystem of information. That is why engineers need both technical understanding and analytical thinking.